Okay, everyone. We're starting back the afternoon session with Pedro, who's joining us. We're talking about PX4 in space. Take it away, Pedro.
Thank you. Right, so I'll do a presentation that might be a bit of like what we have visually been trying to see here. At the end, I have a few questions also to spark some discussion, and hopefully we can get some insight on that. So I am Pedro, I'm a postdoc at KTH in Stockholm, and as of recently also a PX4 maintainer. So our work is a lot focused on space robotics and controls. So particularly my background is controls of autonomous systems, so drones, background, and lately into the space domain. So first, before we go into what space robotics looks like, I'll just do a quick and gentle introduction to PX4. I don't know how many people are familiar with PX4 autopilot. A little hands up. 1, 2, 3. Yay, that's good. Okay, so PX4 basically started with like an autonomy stack originally for multi-rotors or drones or quadcopters. And then it slowly evolved into being a full stack, let's say autonomy stack for multiple types of autonomous vehicles. So rovers, underwater robotics, surface robotics, and soon hopefully spacecraft robotics. And it's basically built on top of NATEX RTOS. I'm sorry for the Firefox. Don't throw those questions at me, please. It's DDS compatible, so that means we have internally a module that we can communicate directly over DDS with whatever onboard computer we want to use. And these modules are running fully parallelized, and they kind of look like different control schemes, and we'll go into that a bit later. So because it uses DDS, we can have direct support for ROS2 in specific. So that's a lot used in the academic community, in the robotics community, and also at a certain extent in the industrial community more versed into robotics. It has a lot of hardware support, so you can also, of course, build whatever custom modules you need. Let's say, standard type of hardware would be PixHawk. That's like the one that most people start to use when they use PX4. But we can also use other types of boards, such as the Voxel by Model AI. And actually, this board, this type of hardware, is very soon going to the moon. Not with PX4, but it's going on board the Cadre rovers that NASA Jet Propulsion Lab is sending at the end of the year. So that also gives you a little of an interesting idea of what now space hardware kind of starts to look like. On what comes to what vehicles we can control, so as I said, we can do multiple types of vehicles, multicopters, fixed wings, VTOLs, and recently also underwater robotics. And we are also going into like kind of jetpacks, satellite type of spacecrafts, balloons, and it's very customizable in a way. And in the same way, we also have multiple flight modes. So these allow you not only to have different types of interaction manually, but also to have off-board control, and we'll talk also about that. We can also have different parameters that can be customized, and we also have an integration with the drone code ecosystem. So this means it interacts well with MAV SDK, with MAVLink, ground control, and there's a lot of also interaction with the industry here, and of course with the Linux Foundation. And it is open source BSD3 license, so this can be used for commercial purposes and so on. So how does PX4 kind of look like in the landscape of the Linux Foundation? So we are a quite big project. It's not, of course, as big as many others, but we have more than 13,000 contributors, more than 1 million devices flying it, and we are somewhere in that category in terms of commits and PR issues. So yeah, it's a growing project, and there's a lot of community effort into making it more sustainable and more future. So, but what about space robotics? So here I'm going to go back a bit into like what it kind of looks like from an academic perspective to develop something that at some point you want to test in space. And so generally we kind of start with like some algorithm that we kind of want to test. And this can be for planning, for controls, for estimation, and multiple types of things we can do. So in here you have an example of an entry, descent, and landing algorithm that was being projected. Path planning with information gain. So what that means that if you have a spacecraft with unknown dynamics or unknown masses and you want to understand how to move this safely, you kind of need to first collect some information in order to do it. And on the right side, you see some PROs or passive relative orbits of an inspection task in space and how do this look like. Once we have this algorithm that we have projected or that we have designed, we want to go into a test phase. And the test at first looks like a simulation environment. And this might be MATLAB, might be ROS, might be CFE, might be Basilisk. And there are different types of interfaces depending on the target platform. So here we have the MIT spheres. These were the robots that were for a very long time operating on the space station for guest science experiments. The NASA Astrobee platform, which came right after the MIT spheres, and it's more ROS-based, so also more friendly for guest science researchers to use. And on the right side, you have Basilisk, and especially you have Wizard, which is their Unity-based interface. So all of these simulate dynamics in different ways and some more accurate than others.
Question.
Yes.
Isn't Astrobee running Linux underneath it?
Astrobee runs Linux,
Okay.
Debian-based, and
Yeah.
that's also how you pack the software. So when you build your software package to deploy, you actually build Debian packages that then are installed
Yeah.
on the platform.
Thank
They
you.
have,
Matched my memory.
yeah, so
I wasn't sure if you were talking that all this is NetX or not.
no. Yeah,
Okay.
so at least Astrobee is, yeah.
Okay.
And the Astrobee also has three different processors. The low level, mid level, and high level. High level runs Android, then the mid level and the level run Debian, and they have just different CPU capabilities. And you can deploy ROS nodes on different instances of them, and you usually control them through the Android interface, but they also allow you to have some control over the ROS interface, which is especially nice for guest science. Then we want to go from this type of simulation environment into a bit more of a realistic test, and this will be through analog hardware. So in this case, you have the MIT spheres at the Space Systems Laboratory at MIT. This is how they look like. There you have the ground version of the NASA Astrobee platform. So here, how you kind of mimic microgravity, let's say, that you have somewhat of a reasonable testing, is that the platform is on top of what we call an air carriage. And this air carriage creates an air gap that's about 20 microns with the surface. So at that point, you have no friction with the floor. And if you push the vehicle, it will keep going. Of course, you have some residual air drag, but at this velocity, that doesn't really matter. But this can at least give you a sense of like, how is this actually performing on the real hardware? And on the right side, you have also, of course, CubeSats that now become more and more popular. In this case, it's Carnegie Mellon's Rex Lab that they are working on. So once we have done that test phase, then we actually want to deploy this. And if everything goes well along the stack, then you do it at a certain point, the code freeze. Once you do the code freeze, your code is uploaded. And then you are operating them either on the MIT spheres or on the NASA Astrobee or even on the CubeSat. And in fact, the video here in the middle is a test session that I was doing with some colleagues from MIT, in which we wanted to test some formation control on the Astrobee. So this basically completes the pipeline. So throughout these phases, we want to make sure that the software is good enough that we can be fairly confident that we'll not be wasting 5 hours of astronaut time, which is extremely expensive. And we want to make sure that whatever we tested throughout these steps gives us a good sense of validation as we proceed on the chain. And so towards that, we started to identify along all the ground facilities that exist, what are the main challenges, specifically on the analog hardware. And so the first one was that it was hard to replicate these test beds. So it was hard to get the exact same hardware or the exact same firmware to run in here. The second one was that some software is closed source. So the Astrobee, fortunately, is completely open, and you can even run their simulator on your own computer. But other approaches are not. And so this creates a difference in terms of like accessibility to what we can test. Hard to reproduce results, because if it is closed source and hard to replicate the test beds, then this also leads to how can we ensure that whatever was tested and the papers that we come out with actually still work when we want to retest them or improve on them. And lastly, limited expandability, because if we have difficult access to hardware and software, then it's also hard to increase the usage of these platforms. So based on that, we came up with what we call Atmos and PX4Space, which is a basically open source hardware and software framework, if you want to call it, to do space robotics. So we started by creating the platform that you see on the right, which is built entirely out of commercial off-the-shelf components. So you can literally, if you want to set up your space robotics lab and try to do spacecraft analog tasks, you can build that with around $8,000 or $7,000. We have a complete software in the loop stack. So that means all the code that we run in the simulator is mimicked almost entirely on the hardware. So we stop basically at the driver level. So all the ROS nodes are the same. All the firmware that runs on the microcontroller is the same. And then at the driver's part, we have interfaces through simulators or interface through hardware through the drivers. And on the left side, we also built a website, and the links will be at the end, that you can basically follow a Lego style setup in which we tell you what bill of materials you need to buy and what you need to do at each step, what parts you need to print, what parts you need to water jet, and so on, so that you can replicate exactly the same thing.
You do the software side of it as well, is your software bill of materials equivalent, as well as the hard, as part of that whole bill of materials, it's a true system. Bill of materials is what I'm trying to figure out.
It's hardware bill of
Oh, wait.
materials. Yeah, we do not have yet.
The software
well.
aspect.
Yeah,
into it.
so that was already something that I took a note that might be interesting to see
We'll have to talk
in the
about it.
future.
Yeah. okay.
Yeah. So this, of course, can be used to control analog microgravity vehicles. So what this mimics is basically a satellite reaction control system, and depending on what you put on it, you might be able to control, I don't know, a rocket, or might be able to control other types of actuation in a satellite. But since it's based on PX4, we can also expect that in the future we can try to control different types of systems, such as rovers or landers or other types of autonomous agents that we might need. And so to give a little overview of the hardware, so the platform kind of looks like this. We have three 1.5 liter 300 bar air tanks. So these are basically the fuel of the spacecraft. While we have that, we can keep the floating platform and we can keep moving it. What we do not have that is a big issue in space is slosh dynamics. I don't know how many people are familiar with that, but it just means that when you have a liquid in microgravity, it's gonna bounce around inside your tank.
Yeah.
And this can be very disturbing to your control system. So what people usually do is they minimize this slosh. There are different techniques for that, even at the tank design level. But that's kind of what we have here. Then we have modular actuation plates. So we have 8 thrusters, which are solenoid valves that mimic, again, the reaction control system of a satellite that's used to control attitude and small translation maneuvers. But we can also change that and use propellers. And this would mimic the NASA Astrobee operating on inside the space station. So there are, maybe when I say propellers in a space environment, people kind of look like, okay, but you don't have air, so why would you need propellers? Well, inside space stations and maybe habitats, you will have it. And so you kind of need to deal with that as well. Our onboard computer at the high level is an NVIDIA Jetson RNNX, and we also have at the low level a PX4 6X Mini. So we have this dual architecture. Almost all the hardware interface is handled by PX4, and then at the top part for multiple algorithms, we use the Jetson. And then, of course, it can be also payload capability. So as you see, this is vertically stacked. At the top there, we have a gripper, but that top area, we can also replace it with industry hardware, with industry actuators, with CubeSats that we want to test and mimic a formation maneuver on orbit to see how ranging equipment is working, to see how estimators are working. So this is a bit flexible in that sense. And then the laboratory also provides a motion capture system. So this gives us a tracking below 1 millimeter of error for each rigid body moving around, which is used for ground truthing this entire thing. So then on the software part, and maybe this also goes towards Kate's question, what kind of this looks like. So we built first what we call PX4Space, which started, maybe as many people do, as a fork of PX4 Autopilot. And we started building our control stack there. So all the way from position, attitude, rate controllers, and control location for this type of actuators. From that point, we can also start having higher level algorithms. So we can use advanced control schemes, advanced planning schemes. Some of you might heard at least the terminology of temporal logics or logics in terms of verification and validation for software. It's also started to be used in control for designing control that can be provably safe and even for at the planning level. And because we are running an NVIDIA Jetson, we can of course also use different type of middleware. So you can use F prime, we can perhaps in the future start using space grade Linux. I would be interested in that. And also we have the ability to also use space ROS or other type of OS versions. So to give you just a little glimpse of what kind of this looks like when they are moving around. So this is the two of the 3 platforms we have available in the lab. And soon they will start to move. They need to do some maneuvering going from one position to the other. And this is all done autonomously in the sense that we give them a task specification that says, I want you to be on this and this positions at its time. And this is done for the 2 robots, and the planner layer ensures that one, we are not asking anything invisible, so that we don't ask one robot to be in 2 different places, or that we don't ask the 2 robots to be at the same place at the same time. this is all going all the way down to generating a safe path, let's say. So safe in our context means that we keep the system within a region that it will not collide with anything and will not damage with anything, and we can keep it inside that area of the state space. And this scheme basically ensures that we can do the whole pipeline, let's say, in a safer way and test whatever we need to test. So the team behind this is quite a few people. For the Swedish among you, you might know some of the people in here. For the robotics prone people, you might know some other of the people in here. We basically have 4 PI, so the main PI of the project is Dimus, and then Krister, Ivan, and Jana work with the space, underwater, and planning part. I didn't specify here what's the connection of underwater with this, but the paradigm behind the project is to look at the underwater domain and microgravity domain from the same, let's say, holistic point of view. So we want to do in the same way that astronauts are trained before they do EVAs on the space station. They go to a pool and they are put neutrally buoyant, and then they are trained to go around the space station with that. We are basically having the same facility now at KTH. We just got built a large water tank also with motion capture to do this type of thing. Just next to our space robotics lab, we can run experiments simultaneously, which we'll be doing soon. That's the trigger there. And then we have quite a few people that were working on this as well. Also collaborations from Zurich, Professor Roland Sigurd and Jay Young Lim, also from the PX4 maintenance team. And of course, that all of this is as possible because there's a huge community behind it with PX4. And if this wasn't in place, then building such a thing would just not be possible at all. And we're also happy to say that at this point, we already have 3 universities already not only using, but starting to build their own platforms based on this, which starts to feel like, okay, we can create some kind of, let's say, baseline framework here that we can test everything on. So that's kind of where we'd like to go. Okay, so maybe some questions for you folks. How can we use Linux to bridge certifiable academic and industrial development? So when we start to do work with industry, there's a lot this barrier of like, oh, but you are in an academic setting, so a lot of the things you do we cannot really use, or can you put this in Simulink so we can use autocoder? So how can we use Linux to kind of close this barrier and have an environment in which we know what we need to develop and to put where, so that when an industry wants to use it, it's almost ready. And I think that the idea that Olivier was mentioning of making this kind of guide would be fantastic to go in this direction. And please feel free to come up with different ideas. The other question, which might be a bit more, let's say, bigger, is what is really important to certify? I mean, right now we have Linux being used in Crew Dragon spacecrafts doing autonomous docking on the space station. We have Linux being used in Mars helicopters. So what should we be looking at in terms of certifying that this is going to be safe or safety critical? Should we do the entire spectrum? Should we just look at parts of it? I think this is something that can be interesting, especially now that we can have mobile phones controlling things on other planets and not just this space-grade hardware that has been used for a while. Okay, so with this, I come to the end of my talk. If you want links, discover.io is the project, Atmos is the platform and the guide and so on that I was mentioning about. And then our GitHub, in which we have basically everything that you need to get started, and our research is continuously being put out in terms of the code development, references for reasons, and that's it. Thank you. The time.
We are perfectly on time. We have even time for a few questions. Release. If there are direct question from someone.
Yeah, there was.
Yes.
I have a question.
Yeah.
So I see you have these moving in 2 dimension, but you typically have 3-dimensional problems.
Yeah.
So how to handle this?
Right. So when you are on ground facilities, you can never get away with having no gravity on the z-axis. There's just nothing we can do about that. So the goal of that is that we use the underwater facility to make neutral buoyant the robot, and then we test the algorithms in full 6 off there.
Okay.
And on the space robotics facility that we have 3 degrees of freedom, and we can extend it up to 5. So if we want, we can put some kind of gimbal system to test full altitude. And there what we do is we run exactly the same algorithm, exactly the same code. It's just that when it gets to the control allocation phase, we only trigger the files that we have available. There are ways that we can also get away with just using this plane. For instance, if you want to do like an asteroid mission, a lot of labs will use a manipulator. And then what they do is they move the manipulator in a way that it is always on the same plane of motion as the spacecrafts themselves. So you simulate a section of this 3D environment. Yeah, there's different approaches. You can also build solutions that have like an elevator on the platform. Yeah, it just depends on how much money you want, let's say, put into it. One of the best labs in the world for these type of facilities, I managed to talk with the supervisor, and his answer was that going beyond 3 degrees of freedom, it not always can give you like a super accurate result. So if 3 is like the minimum that he would say is the best result. And then you can, of course, always try to improve. Yes.
Good question. How does this PX4 compares to commercial drones? Big
Right.
vendor like DJI, they have enormous resources. I mean, Kalman filter for stability and such.
Right. So it's hard for me to comment on the comparison with DJI because their software is completely closed source, as far as I'm aware. What I can say is that PX4 is also used a lot in commercial companies and commercial drones, and starts to get used even more. So it's especially with Alterian and so on, also working on that side. I do think that PX4 is as capable, let's say, I mean, and this comes again and again, as the people developing it are. And you can, of course, use the same stack in a lot of the modules we have that work perfectly well for multiple applications. And for specific cases, you might want to do some tuning of either the control part or the control side or the estimation part. And this you can always adjust. And because it is completely open, we, of course, also welcome those changes as long as they are useful for the entire community upstream, which we usually recommend people to do. In our case, when we started developing this with PX4Space, we started on a private fork, and this we did just for speed because we needed to get the lab up and running soon. But once we got something running, our first priority became let's upstream everything because we don't want to be maintaining everything just by ourselves. And that's the powerfulness of having a larger community looking at the same code, ensuring that tests are always checked and so on.
To what extent have you guys documented the requirements and the traceability of the code base?
That's a question that would be better targeted for the architecture people at PX4. So Daniel Agar probably would be a good person.
Because if we're starting to look at surfacing the metadata to link in with Linux, then we have the requirements for Linux, and this becomes a system that we can start to reason about. So that made to your earlier question about how we could work better with Linux and other things, is getting your requirements surfaced, then the testability surfaced and linked, so that we can all start to talk the same language.
Yep. I think that's great.
Okay.
Thank you.
Thank you.
Okay.